Hi, welcome back to second part of Evolutionary Neural Network. As promised, this is the practical part where we bring a simple neural network. We train it with a genetic algorithm. So neural network have been used to solve many problems in real life, but it has some limitations due to backpropagation. Backpropagation cannot find always optimal weight matrix that can get you optimal solution for the network. And this is all because the learning algorithm of backpropagation works with gradient descent derivative. However, in this practical example, we are avoiding using backpropagation. In earlier videos, we have a training neural network with backpropagation, but this one, a trained neural network with genetic algorithm. So here is the cycle. For example, we have three networks. These are the three networks, one, two, three. Each one of them, we check, we feed input, and we try to find mean square error, the output of the network. And you can see 33, 30, and 36. Now, these, they will be evaluated. The good networks with minimum fitness will be selected, and the bad ones or the poor ones will be rejected or removed. Then from the best ones that were selected, we will do crossover between two parents and we get children or we get child. And then we do mutation on them to improve their performance. Then they go to next iteration. They save after the next iteration. And then again, we will find the mean square error, evaluate, crossover, mutation, and so on and so forth. So this is the basic cycle of evolutionary neural network. Here we have a setup, a full setup of network. We have X1 and X2, two inputs, two hidden neurons, and one output neuron. Now we've got 9 chromosomes, weight 1, weight 2, weight 3, weight 4, weight 5, weight 6, and bias 1 for hidden neuron 1, and bias 2 for hidden neuron 2, and bias 3 for output neuron. So here is the structure of the network, two inputs, weight matrix, X1 to H1, X2 to H1, X1 to H2, X2 to H2 with their weights. So sum of the inputs multiplied by their weights. And then we get the output, and then the output will be checked by mean square error against the target. And then instead of backpropagation, we use genetic algorithm to train this network. So here is this chromosome of the network that we have. A network means this, the chromosome means the weight matrix of the network. So the chromosome means the weight matrix of network. That's the chromosome, the weight matrix of the network. Now, here is the training set. If it is 0, 0, then it gives you 0. If it is 0, 1, it gives you 1, the target. If it's 1, 0, 1, 1, 1, 0. This is kind of XOR problem. It cannot be solved by a single layer. We explained this one in earlier videos, that single layer cannot solve XOR OR problem. XOR problem cannot be solved by a single layer. You need multi-layer perceptron, or you need to check with the activation functions. So the summary of the network, we have two inputs, two hidden, one output. Sigmoid function can be used for activation function. And we have three bias weights, two for first hidden layer and one for output layer. So that is the net calculation for hidden one a net calculation for hidden 2, and the output layer. Mean square, it's 1 over 2 or 1 over the sample, then t minus target over to square to square to the power 2. Now, sigmoid function, that's the idea of the sigmoid function for activation. It's very obvious. And then input to hidden weights, hidden to output weights 5 to 6, and biases that we have, and bias at the output 3. Now, this is the whole information that were segregated in different slides and explained about it. So this is the input will be fed to here, and that's the weight matrix for the whole network. And these are the net to the hidden, and the net to the output. Now, this is your input or our input in this example. Let's say we take, here we have how many networks? 1, 2, 3, 4. Imagine we have 4 networks. Let's take network C, that example. So this is the weight matrix for the network. That's network matrix for the network. So we will do forward pass. We have input 0, 0, first input. So 0 by anything, you get 0. 0 by anything, you get 0. So what we have bias 1 and bias 2. Put it under the sigma. That's the result for hidden layer, and this is the result for output layer. Now, this is the mean square error. You will have the 0, 0. We have the target of it 0. That's the t, and these are the input 1. That's input 2. The target is 0. So that is the mean square error, 0.183. That's what we get from feeding the first input pattern, which is 0, 0, to network C, that network, just for example. So we fed it. We do the same. The second sample, 0, 1, feed it to the same network. That is the result. Simple calculation. Sum of input multiplied by their weights. Activate them with sigmoid and get the results. This one done in earlier videos. So that's the output for the hidden, for output, and that's the mean square error. We do the sample tree. Sample tree, same thing. That's the input to the hidden, so the output, and mean square error. With sample 4, again 1, 1. Then that's the output. That's the error. And you can see that we have net mean square error. Sum them up. So error 1 plus error 2 plus error 3 plus error 4 over number of samples, 4 samples. And that's how we calculate. So that's from sample 1, that's from sample 2, sample of input, and that sample of 3, and sample 4, which is 1, 1, sample 3, 1, 0, sample 2, 0, 1, and sample 1, the input 0, 0. So that's mean square error that we get for the network. Okay, that's for iteration 1. And we see for the network, and the samples that 4 samples to network A, that's mean square error. 4 samples we fed it to the network B, that's mean square error. 4 samples to the network C, that's mean square error. And 4 samples that were fed to the network D, that's mean square error. Now we select the best mean square error, and the best mean square error means that the minimum mean square error. Well, the minimum mean square error here we have, I think, the least one. Okay, the least one, it will be 0.25, 285 and 0.35. So let's say, so we will select C and D. C and D will be selected, and 0.52 is big, and 0.91 is big. So network A cannot be selected, and network B cannot be selected. Only C and D selected. So we select C and D. Now, that's network C. That's the bias of it. That's the weight and bias for it. And this is the weight matrix. The weight matrix for C is this one. And the weight matrix for D is this one. From the diagram that we have. Now, if we follow the pattern, okay, so if we follow the patterns, these are the parents. Now we need to make kids. We need to bring offsprings. Now, if we have this pattern from the parents, I mean, you have CD, parent 1, C, parent 2, D. So from parent 1, we will use this pattern, C, D, C, D, C, D, C, C, C. So in other words, C means I take zero point 0.9 from here. D, I take zero point 0.6 from here for the child. C, I take zero point 0.4. And D, I take minus zero point 0.5. And C, I take zero point 0.1 from parent C. And D, I take zero point 0.4. And C, 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 it means I take minus 2.10, which I put them as it is. I created child 1 with that pattern. Now let me create child 2 from a different pattern. This pattern, kind of different. I'll say D, C, D, C, D, C, D, D, D. It means what? I'll take D, gene D, minus zero point 0.4. I'll put it as a child 1. And I'll take C, minus zero point 0.2 from child 1, from parent 1 to child 2. And I'll take 0.2 from parent D. C, D, C, D, C, D, C, and D, D, D. So that is child also created. Now we've got two childs, okay, end of iteration. And we feed inputs, again, 4 samples. We have C, parent, we don't do anything. And we have D. Now child 1, we receive, when we submit, for example, here I didn't show the calculation. So 4 samples of input. Samples of input fed into child 1 network and child 2 network. The mean square error found 0.3 and 0.42. So kind of we have reduced, there's some improvement. There's some improvement. 0.3 is improvement for child 1. Now you can see we in the second iteration we selection parent C and child 1 is selected, okay, and then we do crossover between them, okay, and then again we do so if we do crossover between C and child 1, we receive 2 childs. So here's the point for making crossover. So this part with this part and this part with this part. So now we can create child 3 and child 4. And then here mutation, we can we can take D. We can take D. D was this 1.35. We can do mutation. Mutation means that we implement the operation of mutation within one solution, within one child, within one chromosome. Let's take D and we try to mute it to D dash mutation. So D dash is a copy of D, but then we change this bit, for example, randomly, and we change this bit. So 2 bits, 0.2 changed to 0.3 and 0.3 changed to 0.2. So that is D dash change. Now, if we feed samples of input to this network, you'll have a different mean square error, definitely. And now we can see D3, we have less 0.3 improved when we pass the input to the network. So this is more or less in the iteration two. The good ones will be selected, the bad ones will be kicked out, the good ones will be crossed over, and the child will we will implement on them mutation. And then final results, excuse me, best initial was 0.285, and best final, it's kind of 0.19. So the mean square error, slows down with the iterations. So as the iteration, that's the iteration, and this is mean square error. So the error gets down as you go along through the iterations. That's more or less about how we are going to train evolution neural network, simple neural network structure trained with genetic algorithm, inputs fed into network, sigmoid function and output, then hidden layer computation, output layer computation, mean square error, and then mean square error selected crossover is done by genetic algorithm. Mutation is done by genetic algorithm, and the selection for fitness function best mean square error is chosen. Now, without using gradient descent, without using any derivative, um, delta E over delta W. So there's no chain rule, no back propagation. Uh, Thank you very much for listening and watching this class. Stay tuned for the more classes on evolutionary neural network.